Okay, so last time we were talking about how to get the profile of velocity in the case of turbulent flow. So for a laminar flow, we have learned together how we can find analytical solution. For example, if you have a laminar flow in a duct, you can prove that you have a parabolic profile. Okay. Now, in case of turbulent problem, we have a lot of challenges that makes the analytical solution sometimes impossible. This is why we do experiments. Okay, so we say, for example, I have a duct and I want to find how the profile of velocity is. I expect that it will be closer to the flat profile as Reynolds increases because the viscous effect will be reduced. So what we can do then is to say my purpose is to find u as a function of y in case of turbulent flow. So I should ask myself, what are the parameters that can affect the velocity profile? So first, since I have a flow, I can say so I need as parameters rho and mu. And since I want a u function of y, I know that in general, I based myself that the shear stress on the wall, which will account for the viscous effects that will affect the flow behavior, is mu del u by del y. So in order to know if you want how the profile of velocity is varying, I need to have information about the shear stress on the wall. So this is why we say then I can consider additional parameters which are u and y, of course, because my purpose is to find u function of y and the shear stress. So if I consider this is a problem of chapter 7. If I say I want to do an experiment to get the profile of velocity in a turbulent flow, I put my main parameters. So here my main parameters n equal to 5. Okay. I can select independent variables. So as usual, we can try to, we should put units. If you remember, we put units, we see the number of dimensions. So here we can select, for example, let's say we have a row, we have a mu, okay, and we can select the shear, for example, as independent variables. Why we can do this selection here? Because what is our purpose at the end is to find u function of y. So we can consider if we want to perform a dimensionless analysis, we can come up, if you want, with a, a dimensionless number u star related to velocity and a dimensionless number y star related to y. Okay, so this is our purpose at the end. هلا you can هن مثلا for example here they propose the name هن سموهم u plus y plus. You can do what you want. مهم تفهموا شو عم يعملوا. هن قرروا يسموا الباي groups u plus y plus and they want to find what are these groups. If you want to find what are these groups, you use chapter 7. If you use chapter 7 and you do the dimensionless analysis, you will get that the first group, okay, is u times rho to the power 0.5 over shear stress to the power 0.5. You can try it as application on chapter 7. Okay, so you can say now from this definition, you can say that this number, okay, this this should be of dimension of 1 over velocity. This is why we can say that we can define a characteristic velocity u star. Okay, if you remember when we did at the in the previous chapter, we said in order to come up with dimensionless numbers or dimensionless equations, we should define scaling parameters. So here the scaling parameter for velocity, you can define it from the group, from the pi group here. U star is tau over rho to the power half. This is called the friction velocity. It has the unit of a velocity and it is related to the shear stress at the wall. Okay, and if you form the group for y, if you do it, you'll find that y, okay, over mu. What is mu? You have two mu here. You have, this is the dynamic, this is the dynamic viscosity, this is the kinematic viscosity. They are related together. So the kinematic viscosity is the dynamic viscosity over rho. So here, if you do your group, you form your group between rho, tau, and u, which are the independent, rho, tau, and the third variable we said it was mu. Okay, you will get that your result will be the following. You have y times rho. Please try to do it as a practice, to practice on groups, over mu, okay, and times tau to the power 0.5. هلا هي بيطلع لكم here rho to the power 0.5. هلا هن كيف رجعوا قسموها؟ جربوا يقسموها تيبينوا الفريكشن velocity in this expression. إذا بتطلعوا بهالexpression already you have tau to the power 0.5. Okay, so if you divide, if you want to appear rho times rho to the power 0.5 the denominator, then you should have here should multiply by rho 0.5 بصير عندكم rho فوق. ساعتها قالوا انه this term هو اليو ستار تبعنا. Okay, I can replace it by u star, characteristic velocity, هي friction velocity, and this term rho over mu is 1 over the kinematic viscosity. And just this is a simplification. And after getting the group, they found out that they can write the dimensionless group for y is y times u star over kinematic viscosity. What is the importance of this result? This result will tell us if you want experimentally to draw the profile of velocity, we can create a dimensionless number u plus for velocity and a dimensionless number y plus for y, and then we can draw how it's varying. Yani you can deduce from this, yani if you get u plus and y plus, if you know u plus, and of course you can measure u plus is u over u star. U star is measured experimentally. So when you perform experiments, you can get all these variables. You can get what is tau, you have your fluid, you know what is rho. So from the experiment, from this general experimental result, because it's relating dimensionless numbers, you can know what is the profile for it for any turbulent flow u function of y, because you can say that this is a general behavior and I can apply it. Yani I just have to compute what is u plus, what is y plus. I say then it should follow this curve. Okay, and I can then if I change rho, I can determine what will be the effect. If I change the shear stress, what will be the effect. So this is why, as I told you, we do dimensionless analysis to be general, to be extrapolated to the same case, of course. And we should have a turbulent flow. Let's say if this experiment is performed in circular ducts, I can just extrapolate it for turbulent flow in circular ducts. If you remember, at the end of chapter 7, we have seen that Schur condition to extrapolate result should have similarity in geometry and kinetics and kinematic similarities. So the condition is to have the same groups. If you have the same groups in the model and prototype, you can extrapolate your results. So this result, if it's based, let's say, on a cylinder, on a circular duct, turbulent flow in circular duct, then you can use it for any turbulent flow in a circular duct. Just you should compute your dimensionless numbers. Okay. Now, this is how we can determine the profile of velocity experimentally. Now, By experiment also, as you can see, for example, they found out that for circular ducts, okay, this profile is nearly, uh, if you want higher is the Reynolds number, it will be close to the uniform profile. So the viscous effects here will be damped as the Reynolds number increases, okay, because this is called the log law for velocity profile, and it describes the velocity profile near the wall of the pipe. Now, also, we have experimentally shown that the roughness has an effect on the velocity profile. So if you vary the roughness of your pipe, then the velocity profile will be affected. In order to include this parameter, يعني then for example the previous analysis done should be extended. يعني نحن عملنا analysis for smooth pipes قبل. If you want to include the roughness effect, you should add to your variables, you should add epsilon, which is the roughness, okay? And then also we have seen that the diameter of the, when we want to include the roughness effect, we have experimentally observed that the diameter of the pipe will affect also the result. So you can show that you can add a dimensionless number to your numbers, which is epsilon over d, okay? And then you can see for different values of epsilon over d, how your profile will vary. So all of this is performed experimentally. You can draw different graphs for each value of epsilon over d. You can draw a graph, okay? Now, and just what I want you to understand, how we are using the chapter 7 analysis in order to treat turbulent flows. So in this chapter, we'll see now a very important chart, which is called the Moody chart, that is using dimensionless analysis to compute the behavior of turbulent flows. We'll introduce it in a while. So, and just a small remark, as you can see here, the viscous wall unit L star, which we defined. We defined a characteristic length L star. Y plus is Y over L star, and L star is the kinematic viscosity over the friction velocity U star. As you can see here, L star was found to be, which is the characteristic length, was found to be from dimensionless analysis equal to mu over U star. So here you can see that, okay, when U star increases, and U star will increase with, U star is the characteristic length related to the shear stress and to rho, okay? Whenever you have that, when Reynolds number increases, what will happen? When Reynolds number increases, okay, you have that, we will see that the shear stress effects will be reduced, okay? Why? Because as Reynolds increases, the viscous wall unit L star will decrease, okay? Because when, as we have defined L star is inversely proportional to U star, okay? And so higher is U star, and U star is related to the Reynolds number, lower will be the value of L star, okay? Why U star will increase with Reynolds number? Because you know that shear stress is related to what? Is related to the variation of U with Y. When you have a high Reynolds number, okay, so shear is mu times del U by del Y. When you have a high Reynolds number, this will tend to have to lead to a high gradient of velocity. Yani you will have you will not have a very smooth variation, because when you have inertia force or dominance, you have very large velocities. This will tend to vary U in a fast way, and if U is varying in a fast way, this will lead to a reduction of the value of L star. and then the viscous effect will be less dominant. Inertia effect will overcome viscous effect. Okay, so now in the following, I know that it might seem that this is complex, but you will see that when we apply these results, they are really simple. Okay, so we will understand more all of these when we do problems. Okay, so the idea now is to see the effect of all of these parameters on the flow behavior of a turbulent flow. So you should first know until now that for a turbulent flow, the roughness effect is important, the Reynolds number is important. Okay, and then we can define, as we said, from experiments, we can define profile of velocities for turbulent flow. For example, if you remember in one of the problems we did before, I told you I will give you the profile of velocity for turbulent case. And if you remember, it was in one of the review problems. It was for a turbulent flow in a circular dog. The velocity profile was uh, U average over VC, where VC is the center line velocity, which is the maximum velocity, equal to 1 minus R over R to the power 1 over N. And N was equal to 7. This N is determined experimentally, okay? And N is a function of the Reynolds number. So the value of N will change with the Reynolds number. And this is one of the most used, we call it 1/7 power law velocity profile. For high Reynolds number, if you draw this profile, it's very close to the flat profile. So n equals 7 is for the case of high Reynolds numbers. For smaller Reynolds numbers, you'll have different values of n. Okay, so this profile is determined by experimental analysis. And we can see that as Reynolds increases, the profile will go from the parabolic profile of laminar flow, and it will tend to a flat profile following the 1/7 power law velocity profile. Now, if you remember, last time we defined the friction factor for cases of laminar flow. And we were able to do analytical calculation to find the friction factor. What is the friction factor? The friction factor is related to losses, okay? To major losses that we can encounter when moving in a pipe. So we have seen that when you move in a pipe, okay, you have losses due to friction. And to overcome these losses, for example, if you have a horizontal pipe, you should create the gradient in pressure, a pressure drop that will be able to overcome friction. Now, in analytical cases, we were able to compute the friction forces analytically, while in turbulent cases, it's not simple to do it. This is why we defined a dimensionless number related to friction, which is F, okay? And if you remember, we defined last time what is F. We'll see it in a while again. So F is related to losses HF, which is the head loss due to friction. And we can show that by performing experiments, we can relate this friction factor to the Reynolds number, and if a pipe is smooth, and to Reynolds number and roughness if a pipe is rough. Okay, so first, always we should pay attention for roughness, because roughness will affect the behavior of the turbulent flow. If you are treating smooth pipes, we can experimentally develop empirical relations between F and Reynolds only, but we'll see after that for the case of rough pipes, we should add a parameter. In addition to Reynolds number, we should add epsilon over D. Okay, now let us see this. So all of these results are just curve fittings results. And how they got? Prandtl and Blasius, how they got these relations? They performed experiments. They said that if we do the pi group analysis, one group is F, the friction factor, another group is Reynolds number. If I perform an experiment and I draw, let's say, I draw the profile, okay, how F is varying with Reynolds, I can do curve fitting techniques and give an empirical relation. You will tell me why we have different results, different empirical relations, because you know that you have variable fitting techniques. And when you perform fitting techniques, you can end up with several empirical relations. Now, which one is better? It depends on experiments. And in general, we say, for example, for each empirical relation, we give the range where it's applicable. This expression, for example, is valid for Reynolds between 4,000 and 10 to the power 5. We have found another behavior for higher Reynolds number, for example. Okay, so each empirical relation should be provided with a certain interval. And here, for example, they are not specifying a certain interval, so you can work with it for any value, but maybe this is more accurate because it's dividing the intervals for Reynolds. Okay, and with experience and with time, we have seen which one is more helpful. In general, for smooth pipes, uh, we prefer to use a more general result to include the case of rough pipes. This is why the most used relations are not these. Moody, a scientist called Moody, developed a relation for turbulent flow, and we will see in a while what was his relations. And in this chapter, we will mainly deal with Moody results. Okay. Just this is for you to know that you can have different empirical results because of the variable fitting techniques that can be used. Now, we have already defined, as we said, the friction factor. The friction factor is a dimensionless number related to the friction head. So F is equal to the friction head, HF. If you do a dimensionless analysis, you can find this group, okay, times 2G D over LV square. And we have seen last time, okay, how we determine this expression. And of course, we have seen that the friction head should be balanced by a pressure head. Okay, so the pressure drop will be the driving for the flow. Of course, if I'm considering a horizontal pipe, okay, and we have seen what to do if we have a vertical pipe. If we have a vertical pipe, we can put the modified delta P accounting for gravitational effect. So of course, if you have a flow moving down, the gravity will help you into moving your flow. While if you move up, you should overcome, in addition to friction, you should overcome gravity. So this is why we defined last time a modified delta P accounting for gravity effects in case the pipe is inclined. Okay. Now, we can see that in order to take into consideration, in order to come up with a certain estimation for delta P, okay, what we did here, we said that the friction factor was found empirically from Blasius result. Let us replace F by the value found by the scientist to have an idea how the pressure drop is varying with the velocity of the flow. And if you replace your friction factor from this slide, the previous slide, the empirical relation of Blasius is that for Reynolds number between 4,000 and 10 to the power 5, I can replace the friction factor for a smooth pipe by the following result. Okay, so if you just replace in this equation, you will see that your delta P is proportional to V to the power 7 over 4, while the expression we developed last time for the pressure drop required to overcome friction was proportional to V. This indicates what? This indicates that with turbulent flows, okay, to drive turbulent flows, we need a higher pressure drop because the proportionality, يعني if you want the rate of increase with V is higher. This is why we can now understand what we observed in this graph last time. If you remember last time, I told you if we draw the variation of delta P function of V, we can see that after a certain Reynolds number, the behavior will completely change. First, it was nearly linear in the laminar region. And after this, we start to have a high increase in the slope in the transition region. And at the end, we have nearly delta P proportional to V to the power 1.75. This is in confirmation with the empirical formulas obtained by the scientists. Okay, so at the end, in case of turbulent cases, the strategy was to perform experiment and come up with empirical relations that can be generally used. Now, in practical cases, what we will use in this chapter? Okay, in this chapter, we'll see how to deal with turbulent flows of in ducts of a certain roughness, how we can compute the losses. Okay, this is the main purpose of this chapter. So here, for example, they show you the important parameters affecting the turbulent profile. First, you have to account, you should find what are the losses. To compute the losses, we define the friction factor, which is the dimensionless number related to friction losses. And as we said, we have observed the importance of Reynolds number and the importance of epsilon over d. So the strategy is, instead of developing empirical relations that are complex to use, we can use graphs. So these scientists will perform several experiments for different values of Reynolds, F, and epsilon over d. And they will be able to draw these different graphs. For example, how they do this? They can vary the Reynolds number for a certain epsilon. They fix first epsilon over d. They vary Reynolds, they measure F, so they can plot one of the curves. Then once they are done with this curve, they change epsilon over d, and they change again Reynolds and draw another curve, etc. And why these results are general? Because they are working with dimensionless numbers. So as long as similarity conditions hold on, we can use these charts. Okay, and this is what we call the results developed by the scientist Moody and drawn in a graph was called Moody charts. We have different scientists that worked on this. You can have different graphs, but the most used one who will Moody diagram. Okay, we'll see it together. So here you have different relations developed in literature. Don't worry about them. I'm just giving these relations for you to know that several researchers worked on this. But mainly, what you will work on is the result of Moody. So the most used diagram and most famous chart, but it's not the only one, is the Moody diagram. And the Moody diagram is based on the following empirical relation. So you can always work or with the Moody or with the empirical relation. But why we prefer Moody? Because this empirical relation is not straightforward. Okay, it's not a if I want to calculate analytically, it is complex. And if, for example, sometimes Reynolds is function of D, if D is unknown and I want to get D using this relation, this is quite complex. I need to have a powerful calculator to be able to solve it. Okay, or I should do trial and errors. To avoid this, we use the Moody diagram. Okay, so the Moody diagram is just plotting this empirical relation. And this empirical relation was obtained from curve fitting techniques. Okay, so now how to use Moody, and what is Moody diagram? This is the Moody chart for turbulent flow. Okay, and also in this diagram you have the case of laminar flow. So if you remember last time we developed the analytical solution. Of course, this is for circular ducts. Okay, this diagram was developed based on the following geometry: circular ducts, and we varied the velocity of the flow, or we varied the type of the flow anyway to vary Reynolds number. Okay, so we varied Reynolds number, as I told you, for different roughness scales, for different values of epsilon over d, and we measured the friction factor. So as you can see here, on the horizontal axis, the dimensionless number of interest is the Reynolds number. On the vertical axis, you have two parameters. You have here the main vertical axis, you have the friction factor, and you have also here different values of epsilon over d. Okay, so here you have epsilon over d. So how we can use this chart? For example, if you have a flow and you know the value of Reynolds number and you know the roughness and diameter, you say, let us say, for example, Reynolds number is 10 to the power 5 and epsilon over d is 0 point, for example, 002, for example. And I want to find what is the friction factor. I come to Moody chart. I say this is I draw a vertical line for corresponding to Reynolds equal 10.5. I search for epsilon over d equals to 0.002. It's here. I follow the curve, the intersection point here. Okay, I find it, and then I can read by taking a horizontal line. I can read the friction factor. The friction factor is 0.025. So F will vary with both Reynolds and epsilon over d. If one of these two will vary, F will vary. Okay, so if you have, for example, several pipes in series connected by fittings, you have different friction factors in each zone. Because here, for example, when you have change in diameter, the Reynolds number will change and epsilon over d will change, which will affect your friction factor. So if friction factor will remain the same as long as the Reynolds number and epsilon over d are not changed. So if you have one circular duct of constant diameter, okay, then you can find one friction factor for the whole. Of course, if you consider the case of a fully developed flow, so V average is not varying. Okay, here in this Reynolds number, you use the average velocity. The average velocity in your flow. Okay, so if V is not changing, the D is constant, and I have a certain pipe roughness epsilon, then in this duct I can compute what is the friction factor. Okay, now sometimes it might be challenging to use Moody. Why? Because the example I gave you is the easiest one. We know Reynolds because we know, so to know Reynolds we should know V. So Reynolds is rho Vd over mu. To know Reynolds, you should know the velocity and the diameter, and of course the type of your flow. And to know epsilon over d, of course you should know the pipe material, because the pipe material will affect the roughness epsilon. And the geometry of the duct, the diameter of the duct will affect epsilon over d. So now, let us say d is unknown. If I don't know d, this is challenging. Why? Because then I don't know epsilon over d and I don't know Reynolds. So, but in the Moody diagram, I need two inputs to get the circle. So what can I do in this case? The only thing I can do in this case is to assume. I assume d, okay? I assume d, and I should perform then several iterations to end up with the actual value of it. Okay. Now you will tell me what will I use, which equation will I use? Of course, when you do an assumption, you should write equations, replace d in these equations to get your the values of velocity and the values of Reynolds and the values of epsilon over d, and then you can come to your Moody chart, okay? And for this d, once you assume d, you can get Reynolds number, let's say. You can get epsilon over d, you compute f. So now, how can I know if f is right or not? I should compare the f I got from Moody with the f I calculated from equations. And I continue to do this procedure until convergence. Now, this might again I tell you this might seem complex for you, but now when we start with problems, you will understand everything. So what I suggest for you is I will post as usual several problems for you. I suggest that you start by problems, then go back to the course, because this will be helpful. Because now maybe it will seem for you that we are talking about something very complex, but once you see it in practice, it's really simple. Okay, so we'll do some examples together to see how to perform this procedure. So this is the iterative solutions that they are talking about. Sometimes, okay, as I told you, you have the diameter unknown or the flow rate unknown. This is challenging cases, and these cases require iterations. When only f is unknown, it's simple because you know Reynolds, you know epsilon over d, you get f by one iteration. Okay. However, in case you have the pipe diameter or the flow rate unknown, then you should go through an iterative process to solve. And what is the algorithm in general? Uh, for the gas, you can guess the friction factor or you can guess the diameter. Which one is better? Also, you will understand this with problems. When we do problems, you will know how to do educated guesses. Okay. Uh, so I will leave this to problems because when we do problems, we'll understand what do we mean by the educated guess. So, for example, you can guess the friction factor. And when you guess the friction factor, you will compute from equations. Now, which equation I'm talking about? As you know, whenever you have a fluid problem, the first equation you write is continuity. Continuity equation for your flow. The mass flow rate is constant. If we are working in a flow, so we know that always, in case we have a steady process, that m dot n equal m dot out, or sum of m dot n equal sum of m dot out. So the first relation you can write is continuity. Continuity will allow you to relate velocities. Okay. The second relation you can write is the energy equation. Okay. Now